To understand how the geosphere exchanges carbon with the other reservoirs, we need to remember a little bit about our plate tectonics. So we know that the sediment on the ocean floor has some organic carbon from dead critters that have fallen to the bottom of the ocean. And if we think about our oceanic lithosphere, we recall that oceanic lithosphere is denser than continental lithosphere, and so we know that it's going to subduct. So eventually some of that organic carbon will be subducted into the mantle through this process of subduction at convergent plate boundaries. So we also know that at convergent plate boundaries, we have a lot of volcanoes. And so the addition of water to the mantle and also other volatiles like carbon causes melting in the mantle and causes a lot of volcanoes to form above convergent plate boundaries. So some of this carbon will be released into the mantle and ultimately erupted at volcanoes and released back into the atmosphere in the form of CO2. But not all of that carbon will be released in volcanoes. Some of it will be transported through subduction into the deeper parts of the mantle. Deep in the mantle, that carbon can remain for hundreds of millions of years until ultimately it might be released from the mantle at divergent plate boundaries. Divergent plate boundaries are also sources of volcanism, right? So there are underwater volcanoes at mid-ocean ridge spreading centers that are releasing CO2 directly into the hydrosphere at these underwater volcanoes. Okay, so similar to the balance between like photosynthesis and respiration in the biosphere and the atmosphere, these processes of sediment being subducted and bringing dead organic matter down into the mantle and then being re-released by volcanoes are generally in balance. However, there's another important interaction between the atmosphere and the geosphere that we've got to talk about. And not all the organic carbon that gets deposited in rocks ends up getting subducted. So there's one other very important interaction between the geosphere, the hydrosphere, and the atmosphere, and that's a process called chemical weathering. Chemical weathering is basically the disintegration of rocks by chemical reactions. Or another way to think of it is how the atmosphere and the hydrosphere work together to dissolve mountains. So as rainwater falls through the atmosphere, it interacts with CO2 that's present in the atmosphere and combines to make a substance called carbonic acid. So that equation can be written like this. H2O plus CO2 makes carbonic acid. Now, carbonic acid is very good at dissolving rock. So carbonic acid combined with water is going to react with minerals, right? So all the different minerals that we learned about at the beginning of class, and it's going to work to dissolve them. And so when carbonic acid in water dissolves minerals, the products are bicarbonate, HCO3, some cations, right? Remember, cations are positively charged ions, things like calcium and potassium that go into these minerals. And then another byproduct is clay minerals. So carbonic acid in water dissolves minerals, making bicarbonate, free cations, and clay. Now that bicarbonate and those cations and that clay are eventually going to be sort of washed downstream in rivers to the ocean. Once that bicarbonate and those cations are washed into the ocean, they are used by critters that live in the ocean to make calcite and eventually limestone, rock, chemical sedimentary rock made entirely of calcite, is going to be deposited on the seafloor. So when critters make calcite in the ocean, they use this reaction is followed. So the cation calcium is consumed along with bicarbonate to make CaCO3, the mineral calcite, which is limestone, and that also releases some CO2 and some H2O. Now, a single generalized reaction can be written that describes this whole process, and that is as follows. So here's the generalized reaction that includes all of these steps. CO2 and H2O combine in the atmosphere to make carbonic acid. That carbonic acid reacts with silicate minerals. This is a formula for the mineral wollastonite, which is actually not very common in the Earth's crust, but it sort of just serves as a simple chemical formula to approximate silicate minerals. So CaSiO3. So this silicate mineral is dissolved by the carbonic acid. Ultimately, it's transported into the rivers, and the released calcium is able to combine with bicarbonate to make calcite, which releases water, forms quartz as well, and releases CO2. So although CO2 is released at the end of this process, this whole reaction actually consumes more CO2 than it releases. You'll notice that at the front end of the reaction, there are 2 molecules of CO2 that are consumed. And at the end of the reaction, we've only got 1 molecule of CO2 that's released. So the net effect is to take CO2 out of the atmosphere and trap it in rocks, namely as limestone. So there are sort of 2 CO2 molecules that go in, 1 comes out, and 1 gets trapped in rocks. Those rocks will be deposited on the sea floor, and it's mostly limestone that we're talking about, calcium carbonate. Now, the deposition of limestone on the sea floor, it doesn't always happen at the bottom of the ocean on oceanic lithosphere. Sometimes the seafloor, in quotes, is actually still on continental lithosphere. It's just continental lithosphere that has been flooded by the ocean. So what that means is that sometimes these limestones, they can be preserved as rocks for hundreds of millions of years, even billions of years. So that completely removes the atmospheric carbon from this system and stores it away as rocks for a very, very, very long time. Just as an example of this, here's a map of the Earth from our textbook. And we see that, there are parts of the coast of North America that are, very, very shallow. So the seas are very, very shallow. And so in these areas that are shown in this very light blue here, this is all still continental crust and lithosphere. So it will not be subducted in the immediate future, right? This is going to stick around for a very long time because continents are more buoyant than oceanic lithosphere. And so these shallow seas on the margins of continents, you can form a lot of limestone in those environments, and that locks away atmospheric carbon in the rock record for a very, very long time. So some other flooded parts of the world, sort of in Northern Europe here, basically on the edges of continents. Excellent example sort of around Australia. All these shallow seas are where we can store carbon in rocks for very, very long periods of time, billions of years even. This is an important concept because at different times in Earth's past, sea level has been much higher. So for example, here again is that paleogeographic map of the Earth from 90 million years ago. You can see that much of North America is sort of flooded by shallow seas. Same thing, with Africa and Europe and Asia over here, right? There's large parts of the continental crust that were flooded with shallow seas, and lots of limestone and calcareous rocks were deposited at this time and preserved, for at least 90 million years. They're there today. We can go look at them. They're above sea level, and they'll probably be there for many, many, many millions of more years to come. Okay, so let's bring it back to this oxygen isotope record of benthic foraminifera and try to figure out how exactly, Earth's climate went from, no ice and tropical plants in the poles to our climate today, which is relatively much more cold, right? What caused this dramatic change in Earth's climate over the last 50 million years? Well, 50 million years ago, something very important happened. About 50 million years ago, India collided with Asia, and the largest mountains in the world, the Himalayas, began to form, right? So if you look at the map of the Earth today, you'll see that the Himalayas are here, and they're at the front of what's called the Tibetan Plateau, a huge area of very high elevation crust, right? This huge area where the mountains have been pushed up due to this collision of India with Asia. So that collision, starting 50 million years ago, has uplifted all of this huge area of rock and exposed it to chemical weathering. So the chemical weathering of all of this bare rock that has been exposed by the collision of India with Asia has been producing this long-term chemical weathering that is drawing down the CO2 content of Earth's atmosphere. But it's doing it very, very slowly, right? It's taken 50 million years for Earth to cool down as a result of this process. It's a very, very long time scale process that causes climate change. Now, there are many different time scales of climate change. This is an example of one of the longest time scales. Many millions of years time scale over which chemical weathering of mountains can draw down global CO2. So if we look back at this figure, the long-term trend towards colder temperatures is probably caused by chemical weathering of the Tibetan Plateau. It really started about 50 million years ago and has caused a long-term drawdown in Earth's CO2, or its atmospheric CO2. That's a greenhouse gas. Removing it from the atmosphere makes the Earth colder. But we also notice in this benthic foram record that there's this long-term trend, and there's also much shorter timescale trends, right? Small wiggles, upturns, downturns that happen on a much, much shorter timescale. So as we move forward, we'll begin to explore some of these smaller timescale changes in Earth's climate and what causes those to happen.